Now let's look at this statics problem. Now the thing to remember when we're dealing with a static system, static means it does not move, is the biggest thing that we have to remember is what does a static system mean? That means the sum of all the forces in the x direction, the y direction, the z direction have to be zero. The moments about the x, y, and z have to be zero. If there is a force imbalance, it's no longer in static equilibrium. It's a dynamic system, and then we're off to a different class. So everything that we're going to do, we're going to have in this term of it is in static equilibrium. So it is not moving. And that is how we're going to be able to find the forces. Now, in this case, I have this rectangular aluminum rod here on the bottom, and, boom, I guess would be the name for it. I have this rod here along the top. And it's all held together by pins, so there's no rotational force there. We're talking about purely x and y coordinates. Now what we want to do is we want to perform the static analysis and determine the internal forces in AB, which is our boom, and BC, which is our rod. Now it's important we're talking about the internal forces. Now there is a big difference between external and internal forces. When you initially look at this, you might sit there and go, it really doesn't matter, it's the same thing. It's going to be very important for this class that we're only dealing with internal forces when we talk about stress, because stress is not caused by an internal force. So what we need to do is we need to find that force on the inside of these different beams, and the way that we do that is we review all the external forces, we set up a situation where we can use these equations of static equilibrium, and then we can make cuts into the material and find out what the internal force is. So what we want to do is we're going to want to do that analysis. So the first thing that we need to do is we need to draw a free body diagram of this structure. And basically what we're going to do is we are going to identify the external forces. So of the entire structure as a whole. We have nothing going on here at B aside from this external load of 30 kilonewtons that's being pushed down. I have a pin connection at A, which means to tell me that I am going to have a force in the y direction. I am going to have a force in the x direction. No moment, because it's a pin, it's free to rotate about that. Once again, at C, I am going to have a reaction force in the y direction. I'm going to have a reaction force in the x direction. But once again, it is a pin, so it's free to rotate about that point. There is no moment. So now that we have this, we can start applying our equations to start solving these variables. And once again, we are in a static equilibrium condition, which tells me the sum of the forces in the x direction, the y direction, the z direction have to be zero. All of the moments, no matter where I go in the system, we sum them up, have to be zero. So sorry about that. So let's go and solve these equations. So for static equilibrium, what are we going to do? Well, there is no z direction force in this problem because it is a completely 2D object. So we don't have to worry about z. And if we did have z, all we'd have to do is add that third one in. So typically, let's start with, I'm going to sum the forces in the x direction. And I'm going to say to the right is positive. So typically what I'll do when I write these equations is before the summation sign, I will show which direction is positive, because as we remember from mechanics, there really is no wrong direction. As long as we're consistent with what we're calling positive and negative, all the signs will work themselves out in the end. So the sum of all those forces have to be zero because static equilibrium, we are not moving. And so I'm going to have Cx plus Ax. There is no x direction force at B, so that would be zero. So if I go and I solve this, it's going to tell me that Ax is equal to negative Cx. That doesn't really help us now, but we'll come back to that. Next, I'm going to sum the forces in the y direction. Those also have to be equal to zero. And I'm going to say upwards is positive. And that's the typical notation. Up and to the right are positive directions. But if we had them negative, once again, it would all work itself out. So as I look in this, I get Cx and Cy and Ay in the positive direction. And then I have negative 30 kilonewtons in the negative direction. And so from there, I still don't have anything solved yet. So I have Cy plus Ay is equal to 30 kilonewtons. Okay then, so now we need another equation. Well, we've finished up all of our x and y's, so let's start taking a moment equation. Doesn't really matter where you take the moment. The nice thing about the moments is if there is no lever arm, that distance is 0. And so what you typically want to do is you want to select a place where you're going to knock out forces so we can actually solve things. So what we're going to do, we're going to take that moment about C. So the sum of the moments, that's too many moments about C. Counterclockwise is positive. That has to equal 0. So why did I pick C? Well, we see Cx is it's pointed, its direction's right through C. So there is no lever arm. That'll be 0. It falls out. Cy, same thing, goes right through C. It's going to fall out. Ay goes right through C. It's going to fall out. We're only going to have 2 different moments then. And the first one's going to be Ax. So we have Ax, and Ax would send it in a counterclockwise direction, which makes it positive. And the lever arm is 0.6 meters. And then we have our 30 kilonewtons. So 30 kilonewtons, it is off of C by 0.8 meters. And then looking at that here, if I hold C constant and just go in the direction of the force, you'll see that's going to be in the clockwise direction, so that's minus. And we've done well here because now we've got one unknown in our equation. So as we go and solve it, Ax, we'll move the 30 kilonewtons times 0.8 meters to the other side, divide through by 0.6 meters, and once we do that, that's going to give us an Ax of 40 kilonewtons. And then from there, so I've got 40 kilonewtons. Let's underline that. So there's the first part of our problem, and then we can drop Ax in there, and that's going to tell us that Cx is equal to negative 40 kilonewtons. And all that really means is we drew the Cx in the wrong direction. So we will end up changing that. And so what are we left with? Well, we can go back to this force in the y direction. We still have this equation of Cy plus Ay is equal to 30 kilonewtons. We still cannot solve that, so we need to go back and do that. And since we're out of our equilibrium equations on the overall system, what we're going to have to do is we're going to have to apply some equilibrium equations on the separate parts. And that's what we'll go and do in the next video.